Okay, welcome. We're going to start by fixing some things from the previous lecture and moving forward. If you remember, so there are going to be a lot of topics. It's going to be potpourri today. Asynchronous reinforcement learning. We'll talk about evolutionary strategies, connections between policy gradients and gradients in the parameter space. So we'll review our likelihood ratio gradient estimator, so you don't need to worry about this. Then we'll talk about natural policy gradients in detail, and we'll touch on TRPO and proximal policy optimization, which are two state-of-the-art reinforcement learning methods, which essentially are policy gradients plus smart choice of the step size, okay? And they are very, very connected to natural policy gradients, okay? So hopefully a lot of concepts will be, kind of cleared up today, okay? We'll clean them up in our minds. Last time we discussed why, when you have on-policy methods, it's good to have multiple threads, multiple machines, multiple agents to collect experience tuples in different parts of the environment. So this is very natural, okay? We all understand this. Of course, it speeds up, of course, stabilized training. We have way more diverse data to take gradients on. There is no confusion there. Then we discussed about this method, this particular paper, which said, okay, forget about experience buffers. Let's have multi-thread, one agent per thread, and let's put them in different exploration strategies. And this is how we're going to parallelize. There's going to be a global network, okay, with parameters, a policy, and the value here in particular will show the actor-critic version, which is the most famous method that came out of this paper. It's called A3C, so we'll see it in detail. And then we have the different workers. So how does the communication happen? Each worker resets its parameters to the global network, okay? Remember that you may need to have two versions once you're doing critic estimation. The same tricks that we have discussed about how do you estimate value functions, right? Using function approximators, you have a target network. The target should not change at every iteration to stabilize training. So you copy these parameters, then the worker interacts with the environments, computes experience tuples, computes gradients, and sends the gradients to the global network, okay? Then a gradient update step is done, and then again the worker copies the parameters. And because this gradient step happens without locking, it might be that different agents, different threads may have slightly different versions of the policy, okay? So it's called asynchronous updates. They don't all together synchronously collect their gradient steps, average, and take a gradient step as if we had, let's say, 8 times or 16 times more data, 16 times larger batch, not from a single thread, but for all the 16 threads that we have in our machine. Make sense? So then it was hypothesized that potentially the fact that different threads, different agents have slightly different policies helps in exploration, okay, and helps collect even more diverse data. So what people did after that, they said, okay, what if we don't do asynchronous updates? What if all the workers, once they compute their gradients, they accumulate them, average, and take a step synchronously, and then all together they copy the parameter weights. So right now we're sure that every agent has the same neural network. Does this make sense? So now everything is the same, multi-threaded, distributed, but it's synchronous as opposed to asynchronous. Okay, and the actor-critic version of this is called A2C. So you may be seeing in the literature A3C, A2C. Well, it's just actor-critic methods. One is with asynchronous updates and the other is with synchronous updates. And the synchronous updates always showed similar or better performance than the asynchronous, because indeed these are all empirical findings, but overall, once we take a step, we like to have a big batch and diverse enough batch. Okay, so of course, if you aggregate all your data, okay, your gradient direction will be way more informative than doing potentially 16 sequential updates where each batch is, kind of biased because it comes from one agent. Do you think this makes sense? Nothing special. It's just I'm replying to some questions from previous lecture. Now, I would like, because in your homework, you will have potentially to implement an actor-critic method, that we go a little bit more details on the implementation side. we can forget for now about multi-threading. We just need to focus about how to implement it. All right? Now, one question is the following. We've talked about policy gradients and actor critics. When is a method a policy gradient? Where we'll call it policy gradient, and where we'll call it an actor critic? It doesn't mind. It's all terminology, but I mean, it's good not to be confused. Okay, not to have. What do you think?
If we get the value function, it's actor critic. If we only get the action, it's policy gradient.
Yeah, so the policy gradients also have a baseline, a computer baseline, okay, which is kind of supposed to be the value function, but this baseline may not be state dependent. It may just be an average, right? Or it may be, yes, an average of your rewards so far, okay? Does this make sense? Once you make this baseline state dependent, so every state has an estimate of that baseline, which is the value function, and you estimate that using a big neural network, either with Monte Carlo, either with TD updates, okay, two different things, whether it's backup updates or just Monte Carlo fitting. Then you can say, okay, I have an actor critic, and this guy is the critic, okay? Does this make sense? I mean, I can have other estimators for this baseline. That's all I'm trying to say. That, for example, averaging the rewards could be one kind of not very good estimate for the baseline, but it's cheap. And this will go under the, policy gradients methods. All right, so that's clear. Let's look at the pseudocode, okay? Now, my question here was, what is the exact implementation for the critic network? But let's start from the beginning. So, okay, sure, we have multiple threads. And what happens is we say T start equals T, and then the actor is going to perform actions in the environment. So the first thing we see is that it's not like we take a step and we send gradients. It seems like we take multiple steps. How many we take? Well, until T minus T start equals T max. So we have a parameter T max that tells us how many steps we'll do before computing gradients. Okay, is this simple enough? So we just made a small rollout, which is T max step long. What are we going to do now? Let's discuss about these two lines. What is the first line? Well, first of all, both look like gradient updates. That's what I see here. Okay. So you accumulate gradients. It seems to me that here's a score function. So it seems to me that these are gradients for the critic, and this seems, for the actor, and this seems to be gradients for the critic. Do you agree so far? Okay. Okay, great. So let's discuss what are we using for the critic network. What is our, estimator for the advantage? Okay, you remember that we said that here we have the score function log of the policy, grad log of the policy multiplied with the advantage. So if you see that here, imagine that this T max was 4, which in fact is not 4, is 5, but it doesn't matter because it didn't fit in the page. The way they compute here the rewards is the following. They start from the end, and then they say that this R will either be 0 if you reach a terminal state, or will be your value function, okay? And then as you go backwards, you add to these rewards gamma, the previous one, plus the instantaneous reward, okay? So this looks like this. For the third state, let's say you ended up at 4. For the third state, you will have the value function of the fourth plus R3. Do you agree that this is a pretty cool target for so then to get the advantage, for the third state, you'll subtract for this, which is the reward you got, minus the baseline, which is the value function for that state. Okay? Now, let's go one step earlier. Okay, that's what we do. We are moving backwards. We went to the end, and now we're going backwards, and we accumulate in this R those values, okay? Multi-step returns, Okay? 1 step, 2 step, 3 step, 4 step, all the steps will compute gradients. So if you did 5 steps, for each of those 4 states, we'll compute gradients. Okay? And what will be your target will be the reward beyond that state. It's not that you have one rollout, you estimate the reward of the full trajectory, and then you plug it. Make sense? We exploit the fact that there's some temporal consequence, okay? And if I'm action 3, my gradient should be moved according to my reward on time onwards, okay? I'm not sure if this detail was mentioned in previous lectures. That's why I wanted that we see it in more detail, okay? If you remember in previous lectures, we said grad log of the policy multiplied with the reward of the trajectory. What we see here is this reward of the trajectory is broken into different time steps, and we accumulate from each step onwards, and we take the gradient steps. Does this make sense? We can spend time here. It doesn't matter. Okay, so here is what we say the baseline. So how good we think this state is. Then we see what reward we actually got. So what indeed that state was under our current policy. Okay, so this is the advantage. And here, this is standard training of that critic, like standard regression, right? Where for every state we try to predict, the expected discounted return. Okay? Using this Bellman backup operator, using these multi-step returns. Okay? So the multi-step returns have different forms depending on if you're state 1, state 2, state 3, state 4, or state 5 of the unrolled trajectory. I wanted to understand this because we're going to have a homework with advantage actor critic. So now it's the right time that we discuss about this in detail. Okay? Okay, so does this make sense to everybody? We have seen multi-step returns before, okay? We take the exact reward, the exact Monte Carlo reward till a particular time step, and beyond that, we say, okay, the episode terminated, I'll approximate it based on my estimate of the value function, okay? And then I'm gonna, for the advantage, I need to subtract the value function of the current state, not of the terminal state. Very careful, right? So I'm state 3. This is my estimation of my future discounted return, and I'm going to supply not the value function of the fourth. This is simply to get my estimate of the reward, rather my value function of the current state, of course. Okay? So this is a state-of-the-art actor critic method. Okay? There are many other variants for advantage that you can use. For example, if you wish, you can have another neural network estimating the Q function and another one estimating the value function. Here, this method chooses to have only one neural network to do value state estimation, in particular the one for the state as opposed to state action, okay? And then uses the Monte Carlo rewards of the current rollout to estimate advantage, as opposed to having a targeted neural network for the advantage or for the Q, and then to subtract Q minus V to get advantage, all right? But all these possible combinations are, all these combinations are possible, but this one is something that worked really well. And based on the results from the paper, this version of actor critic did better than, let's say, asynchronous version of the n-step Q learning, asynchronous versions of one-step Q learning, asynchronous version of SARSA, one-step, n-step, okay? So, it is a method of choice. Does this make sense? Okay, yes.
So if this is all like one network, then some of the parameters in theta V are going to overlap some of the parameters of theta normally, right? So when you just like update them both, like add the gradients, I guess, both, and do it like at the same time, or? Yeah,
so here, that's a good question. So here the way we, present the pseudocode, it appears as theta and theta V, which is the actor and the critic, have completed these joint parameters. In practice, this was not the case. Both of them were the same network, and they had two heads. Make sense?
So you just add the gradient, from both of the gradients that you update the same values of both of them?
Yes, the one updates that head and the other that head, right? So you don't throw both gradients in both heads. Mm-hmm. Does this make sense? But yes, the backbone will accept gradients from both.
Okay.
Mm-hmm. Okay, So let's move on. Evolutionary methods. I want that we discuss what are alternative ways of optimizing policy functions, okay? Imagine that policy is a neural network. How do we find the weights of that neural network? So far, we discussed about policy gradients. Can we do something more black boxy? So far, yes, we assumed that this reward, and we just described an algorithm that did exactly this. When you take a reward from a trajectory, you don't treat the trajectory as a black box. You think that the trajectory has different states. You even bookkeep things about your different states. You think that the environment is an MDP, and I can compute statistics of those states. The black box way of doing it is just that you get the reward from your trajectory, and this is the fitness, the utility of your current parameter theta, and you try to move your theta, the neural network weights, so that these utilities, these trajectory returns, become higher. Okay? And you forget about states, you forget about the value functions. The only thing you care about is how parameters of your network map to, here. How parameters of your network mark to expected returns. And you can do one rollout to approximate this expected, or you can do multiple ones. Then they're going to be more, accurate, of course. Okay? Does this make sense? So the methods we'll see right now, they don't assume anything about the structure of the environment. They don't assume anything about state. They just have one neural network that parameterizes the policy. We change that policy. We do rollouts. We estimate the rewards. And we try to figure out how to move those status. We saw that, yes, so then we discussed about the evolutionary methods. With the general method, it's extremely simple. You start with a population of parameters. You perturb them. You fit them. You select the best ones. You iterate. It's extremely simple, right? Now, and indeed, the things that have been tried in the literature until 2013 are extremely simple. One is this cross-entropy method. It's called cross-entropy method. Is how do you fit a multivariate isotropic Gaussians to your data? Okay, you initialize mu and standard deviation. You sample from this Gaussian different parameters. You do rollouts with your parameters because every parameter corresponds to a policy, okay? So every parameter instantiates some policy. You do rollouts, you top the top k%, you fit mu's and sigmas, and you update. And then we said, there's no reason to use isotropic Gaussian. You can also use a full covariance matrix, and this is going to be called now covariance matrix adaptation, and you update both. Both the mu and the covariance matrix are updated at every iteration. And we said that this works really well for low dimensions, okay, 20, 100. Can we use these methods for thousands or hundreds of thousands of dimensions? That was the question we asked, all right? Now, before we answer this question, it would be advisable to understand the difference between those methods and the policy gradient methods. And now you're going to say, but these are completely different. Well, it's not exactly completely different. In both cases, we're sampling, okay? In both cases, we're sampling. In evolutionary methods, we're sampling parameter vectors. In policy gradients, what are we sampling? We sample actions. We keep the same parameters, but we say, you know what, I'm not going to trust those parameters. These parameters give me some particular set of actions, let's say, and particular distribution. I'm just going to add noise to that output distribution and sample. Okay? All right. So to understand this connection, let's first go and check a different derivation of that likelihood ratio gradient estimator. Our objective that we're trying to maximize is how to sample trajectories, okay, so that we maximize their utility, the utility of the resulting trajectories, okay? And, okay, let's take a gradient. We say a gradient of theta of that expectation of that, the expectation of trajectories. Now, don't worry, now you're going to say, oh, but now we're talking about expectation of trajectories. I know about expectation of actions. What is expectation of actions with the policy? Okay? Because the policy samples actions, doesn't sample trajectories. Well, sequentially, you will sample a trajectory. And you see how we can very easily go from this to, probability of actions. All right? But for now, let's see how simple it is to get to this. This should not be, how to say, a scary equation. Because we can arrive at this equation from all different starting points. Okay? So we have an expectation. We want to take the gradient of the theta okay, of the policy that influence this expectation. And, well, the gradient of the sum is the sum of the gradient, so we push the gradient inside. And then, well, this is theta, right? Not mu. Mu is going to happen later. And then what we decided to do is to multiply and to divide with the same distribution of trajectories, p theta of tau, all right? And then we said to observe that the grad theta of p divided by p is the gradient of respect to theta of the log of that probability distribution of trajectories. Do you agree? Great. And here is the reward of the trajectories, and here is a p. So here again I have an expectation. And so now the sum became back as an expectation. And why I like expectation? Well, because I can estimate it simply by sampling. All right? And, okay, so this is the expectation, but what if, how do I estimate in practice? Well, I generate samples and I sum, okay? And then the intuitive way to understand this is grad log of pi is a particular direction in the parameter space, okay? Well, the policy is going to be there, and you weight those directions depending on it's a weighted sum of vectors, and the weight of each vector is based on the utility, okay, of that, of the trajectory of that policy. All right. So policies that generate good trajectories, we're going to move towards. We're going to try to maximize their grad log. I mean, because the gradient here is exactly by definition the direction that will maximize that log of pi. Okay, and we'll minimize there. So okay, we've seen all this, but this is another alternative derivation. Now, the interesting thing is that very similar thing can happen when we're trying to sample directly parameter vectors as opposed to actions. Potentially, it might be easier if we have them next to each other, like this. So now, our objective is not that we're going to maximize, is over mu. What is mu? Is the parameters of the distribution of the neural network weights. The simple thing to think about is that our neural networks are sampled from a Gaussian, so this mu is as long as our neural network weights, and tell us the, the mean of those weights, all right? And I have expectation over thetas, network weights, sampled from that Gaussian, okay? And I'm trying to maximize the utility of those parameters vectors, f of theta. And I don't care how this utility doesn't have to be differentiable, okay, with respect to theta. And of course it's not differentiable, right? And that's the whole discussion that we have with the score, the racial likelihood estimators, exactly because we cannot take gradients. We cannot take gradients of the reward all the way with respect to the action. Given the action, the only thing we do to get the reward is we sample, okay? So, now, the point of this lecture is to understand that this is like a numerical, this is very similar to numerical methods of estimating a gradient. You say I sample what is plus epsilon, minus epsilon, this is how I estimate my gradient numerically, and I compute a local approximation of my gradient and I take a step. Okay, because I don't have an analytic way to estimate this gradient. And this is great because f of that now can be whatever you want. Now, how are you going to do it? Again, the gradient of mu of the expectation. The expectation is always helpful to put either a summation or an integral so that we make it explicit. We push the gradient inside. Again, here we do the trick that we multiply and divide by this distribution, with our distribution over neural network parameters theta, all right? And we notice that this is the grad log of that distribution. Do you agree with this? And here is again an expectation. And now to estimate this quantity, which is just a weighted sum of vectors, descending, I'm just going to sample from my parameters. So here, I was sampling the trajectories. Now I'm sampling parameters. Okay? And here is the sample estimate. Do you see how simple it is? I'm just going to sample thetas, just going to compute this, and we'll see concrete examples to make this like a super, clear. One thing that I was wondering, are people confused that here we have trajectory as opposed to action? What would be the next step to rewrite this equation here so that we don't see trajectories, we see actions, because our neural networks, right, take states and predict actions. They don't predict trajectories. We need to sample to get trajectory. Okay? What is the probability of the trajectory? Yes?
It would be the product of the transition probability and policy?
Yes, that is exactly what it is. A trajectory depends on what actions you took, okay? And then where the environment sends you under this action. But your theta don't touch the environment. The environment is exactly what it is. You cannot change where a trajectory is going to go. The only thing the policy can do is choose trajectories that are more likely than others that are less likely. Does this make sense? We cannot change the physics. We're just going to try to find trajectories that have high likelihood. And let's see how this is written here. Okay. Here's the sample estimate. Grad log P of trajectory multiplied with the utility of the trajectory and the probability of a trajectory under theta. Theta are the parameters of our policy network, is a product over time steps. Capital T is the length of the trajectory of the dynamics multiplied with the policy. The log of the product is the sum of the logs. We're remembering that we're taking grad with respect to theta. Dynamics don't depend on theta, and so they go away. And now you just have a grad of theta of sum of those actions, and this is what you have. Okay, very simple. So now, this objective that we saw in the previous page can be expanded in this form. And now instead of this probability of theta of trajectories, we have the probability of theta of alpha given S, which is exactly our neural network, all right? Our policy network. Now, you're going to say, oh, what happened to the R of T? What happened to the reward of the trajectory? Well, remember what we did in the A3C. We multiplied the log, the grad log of probability of an action with the utility, the reward that we get, or the advantage that we get beyond that action, okay? There's no reason, there's no reason to keep the utility of a trajectory as a black box, because I'm the last action you took. Why should I take credit for rewards that previous action generated? If you got a huge reward in the beginning of the episode, plus 500, why should this reward count towards, me boosting my probability, which I'm the last action? You got from me, you took 0 reward. Does this make sense? So we exploit the temporal structure there. Okay? Very simple. Okay. Again, this R, let's not confuse, is not the instantaneous reward, is the advantage from that state and action and on. Right? You remember what we wrote in the previous algorithm. All right, so this is it. That's what we have next to each other. Now I just put here the probabilities of actions. And I think this comparison is good to have, because there is nothing magic about this. In fact, there is so much no magic that essentially it very rarely works without having here an estimator, let's say, but just using the vanilla reinforced algorithm. Essentially, what you end up doing is finite differences. And now we're going to see this connection in more detail. But so far, do we kind of understand this derivation so far? What do you think? Shall we? Yes?
So can I ask, what is the main reason to choose the ES instead of GT?
Yes. So what is the main reason to choose it? Well, first of all, it's extremely easy to parallelize it. And then we're going to see this in a little bit, why, and what the workers need to communicate in case of parallelization under PG, which is the first part of the lecture. So, right, we'll compare those. It's completely black box, so it can be used with anything you want. And sure, it's so easy that, if it would work, then I would use it definitely, because then you don't need to know anything, and you don't need to group its states, nothing. Just sample the parameter vectors, and you can put any objective, non-differentiable, no problem. Right now, we are sweating so much, okay, to make our objectives differentiable. The reason we're sweating so much is currently, once you have a fully differentiable objective, okay, always using the take gradients would be better than just sampling, okay? Derivative-free, what we call derivative-free optimization. Now, what I'm trying to say is that for supervised learning, there's no reason to use evolutionary strategies because you have the gradient. Take the gradient direction. And we know that in high dimensions, like neural networks, they have very few local minima, exponentially rare. You're going to have lots of starting points, but people write papers how to get out of the starting point. Now, once we get to policy gradients, there is this lack of derivative between your actions and the rewards. You have actions, and then what do? You sample the reaction, you get the reward. This is not a differential process. I cannot write derivative of reward with respect to action, right? That's exactly our problem, right? If we could do that, I would just take the derivative all the way. If I knew the reward function analytically, I would just, how to say it, take the gradient of it. Do you agree with this? I would just unroll a little bit on time. And to be honest, this is called pathwise derivatives, and we're going to have a lecture exactly on those. Now, ideally, then when we get to that lecture, we'll say, guys, here was the likelihood ratio estimator. Here's something that is not the likelihood ratio estimator because it can, backpropagate all the way through from your rewards to your parameters of your policy network. Right now, we don't have such a thing. We do not know the environment. We don't know dynamics. We do not know the reward function. What we know how to do is you give me a policy, I sample trajectories, and I estimate returns of those trajectories. Do you see what I mean? So then, since this is what you plan to do, since you plan to be model-free, these people say, you know what, all these, so many papers coming out, at the end of the day, if you just do a standard yes, no theory, nothing, you're not going to be too far from the state-of-the-art model-free, sampling-based methods. Does this make sense to you, what I'm saying?
Yeah.
Okay. Other questions? Yes.
A very quick question. Is that theta Monte Carlo estimates of the policy?
Yes, it
of
is.
the policy using
That's what it
Bayesian
is.
methods.
Exactly. Exactly. And now what you're going to say is that, oh, why it is Monte Carlo? Can I have there maybe a critic?
Yeah.
Yes. Good question. Let me think. I think, yes, there are some papers that try to combine those two. All right? Let me think. Now, if you have a critic, though, it's hard to parallelize it, I suppose, because this critic needs to be coordinated among the agents, except if every thread. Because, by the way, I want to say that for ES to work, you really need to have lots of threads, not 6 and 16, like thousands of threads. Does this make sense? We're talking about lots and lots of threads, and we'll see how this is possible because parallelization becomes extremely cheap. The communication between the threads becomes extremely cheap under some choices. Let me think exactly on this question because I'm not sure if in practice this is possible exactly due to the communication overhead. Okay? All right. Great. So let's go one level deeper, if you don't mind. What is the simplest thing? The simplest thing is mu to parameterize the Gaussian distribution over neural network weights. And then the weights are sampled from that distribution. We all know that the normal distribution has some exponent, some parentheses, x minus mu square, right? Divided by 2 sigma square. So if you take the log of this, you get this. What is in the exponent? Does this make sense? Plus constant. Why constant? Because it doesn't depend on mu. Okay, it doesn't depend on mu. Then let's take the grad of the log. Now, don't say why we take the grad of the log, because we're trying to do this expression. We're trying to go ahead and see how this expression is going to look like in practice. Okay, let's go one level deeper on that expression. And I'm saying in the most obvious and general case that everybody's using is Gaussians. We have Gaussians to parameterize our neural networks. And then the grad of log looks as simple as that. And then, if you try to do the sample estimate of this expression, is essentially 1 over 2, y2. We only have 2 samples. If we had n, we will put n here, right? Of the return of a trajectory multiplied with exactly this, right? The return of a trajectory multiplied with grad m of pm. Does this make sense? Great. Now, let's discuss how we're going to be sampling those thetas. How we're going to sample. We say, okay, we have a Gaussian, but how in particular we'll sample thetas? In practice, what do we do? What happens computationally? Well, what happens computationally is that you have access to a random number generator epsilon who is sampled from a multivariate Gaussian distribution that has 0 men, okay? And the covariance is the identity matrix, okay? And so if each time you sample this epsilon vector, you go and do m is pretty long, plus sigma epsilon 1, you will see that if you take the expectation of this, you're going to get mu, so the expectation is good. And if you take the variance of this, because the variance of this is the identity matrix, this is going to be sigma squared. So indeed, your theta 1, theta 2, theta 3 samples under this very simple parameterization are, have the desired distribution you want, right? That's what you want. If you wanted to sample from this Gaussian, that has mean mu, and the covariance matrix sigma square r, okay? Sigma can totally be different for every coordinate, alright? There's no reason to be the same. It's a vector. Okay. This, in fact, parameterization is exactly what is used in all those VAEs, variation encoders, where they do sample and they try to backprobe through the sample. They write this equation there, and this is backprobable. Okay, so the only thing you do is you sample the epsilon. But we may be able to see this in other lecture. It was supposed to be for this lecture, but what to do? There is some stochasticity on the topics. So it doesn't matter. So here we sample the thetas. So now if you plug in those thetas into your expression, what's going to happen? Well, the mu's are going to cancel, and the sigma is going to cancel, and the only thing you're going to get is this. The epsilon vector, the random vector you sample, multiplied with the utility of the trajectories. What does this remind us of? Well, okay, before we say what it reminds us of, this is the general algorithm. Now we know what it is. It's extremely simple. We sample epsilons. These are the epsilons that we're going to use to mutate our thetas. Okay? We evaluate those mu thetas. We compute the returns. That is the utility of the theta plus epsilon plus sigma epsilon. These are the new thetas, okay? And then we update the theta. Okay, we aggregate over the utils of all the, and then we take a step. Okay?
So we only need to know the epsilon.
Yes. We only need to know the epsilon. So what you're trying to say is that if I want to compute this, I just need to know the epsilon. You don't need to send me the theta. That's what you're trying to say. Yes, you don't need to send me the theta now. And this is going to be extremely... Say it one more time. Yes, that's exactly the idea. That's exactly the main idea behind that paper that we're going to talk about. The fact that we're all generated tons, very long, random seed in the very beginning. We're going to share it to all the workers. It's not going to communicate back and forth anymore, and we all know where each one is in this random seed. And the only thing the workers need to send to each other for them to estimate this expression is what? Let me repeat. The epsilon is going to be generated by this random number generator in the very beginning of the training. Each one, we will know how many workers we are to collaborate to estimate this. Let's say we're 1,000. So I know where each one of my 1,000 friends, 999 friends, is with respect to this random number generator. So all of us need to have the latest theta. We all need to have the latest theta. So the question is, how can we all have the same theta without communicating too much between us? Okay? What is that each one of us needs to communicate to the other? I agree. And this has been from the very beginning. So communication means while we're computing, what do we need to send to each other? This happens in the very beginning, so it doesn't compute any overhead. It's pretty big. It's put in your memory, that's fine. So now we all know the epsilons that everybody's going to be using. If you go to the end, you're going to start from the beginning again. Okay? So this has been shared now to everybody. I know what epsilon each one is using, so the epsilons don't need to be sent, and it's good because epsilons are pretty long. They're as long as the network weights. So, but what we need to, then what is the communication that happens between the workers? Why we need multiple workers to do this on board?
That's about you have to compute the returns.
Yes, the returns, right? That's what happens. That each one of us, using this theta that we have, and you know what is my theta, and I know what's yours, but what you do that I cannot do is each theta I have to unroll a lot of things. So we share the burden of sampling from experience from those different thetas, okay? And then each one of us will evaluate this different theta plus sigma epsilon for a different epsilon vector. So now we have 1,000 numbers, right? Scalars that tell us this mutation is not good, this mutation is not good. Then we send them all to each other. So easy, right? The only thing this communicates is one scalar. From me to everybody else. And that's it. Then we compute this. And we all have the same theta without ever sending the theta around or in gradients or something. Right? So this is trivial to parallelize. Okay? Now I'm going to say, yes, of course you need to have a simulator. I mean, you can have multiple robots, etc. It is biologically porous, but in the sense that, we have a population, that's why they call the evolutionary algorithms, right? There is a population, every person has different mutations, different people survive, and, right? Okay, but this is good. But let's think about the following thing now, to see the connection between this and find a different methods. Yes?
Do they all share the same theta t?
Right, we all start from the same theta t. Actually, do you want that we go a little bit down to see this one? Like I have a particular slide. So here we are. Distributed stochastic gradient descent. How would you do stochastic gradient descent distributed manner? This is what we used in both asynchronous and synchronous reinforcement learning in the first slides, okay? Well, we all need to compute gradient vectors and send them to each other, all right? And send them to a central server. Those gradient vectors are pretty big, all right? They're very big. You have one value for every parameter weight, okay? Now, in evolution, yes, we need dramatic distributed compute, but it's much, much simpler. Because if we look at the algorithm, based on exactly what you said, what do we need to send to each other? The theta is big. So ideally, we don't want to send the theta, because if you have 1,000 people sending thetas to each other, I mean, it's going to be lots of communication right there. The epsilon, yes, is the random seed generation, which we can all agree from the beginning. So the only thing we need to say is this R. Okay, R tau is wrong. R theta, okay, F theta, we call it here. So I'm going to change this. But basically, the fitness of our parameter vectors. And this is how the algorithm looks like. Initial policy parameters theta 0. We all have the same theta 0. Okay? Right, so you see, so with known random seeds and initial parameters theta 0. So we all have, essentially we're involving all the same theta. Inside each one of us is the same theta that's being evolved, okay? And the only thing we send to each other is the fitness of the different mutations of the theta, okay? Why? Because we already know each other's epsilons. So if you send me your f of your theta, I know how to multiply it with the epsilon. I know what's your epsilon, okay? That's it. It's like trivial to parallelize. That's the beauty of, yeah, evolutionary methods, let's say, okay? Yep, now. So we broadcast tiny little scalars, and look at this. If you have 14 cores, it takes you 700 minutes to learn how to walk. If you have 1,500 cores, it takes you 10 minutes to learn. This, you're going to say, okay, sure, you have more cores as normal, but the truth is that we don't achieve similar type of speedups when the communication is big, because the communication becomes a bottleneck. Does this make sense? Okay, well, here the communication time that is not the bottleneck. Okay, now at the same time, just to close this chapter, despite the fact it's faster, the experience is wasted. All right, there is this trade-off between, yes, it's fast, but we waste so many samples. 1,000 workers are computing experience. Okay, but if you're in a simulator, that's fine. If you're in a robot, yes, each, it costs electricity, wear and tear of the robot, blah, blah. But if you're in a simulator, it costs you nothing to sample experience. Okay? So it does make sense if you're to use it only in a simulated setup. Okay, great. So we close that chapter now. Yeah, so let's think a little bit about this. So far, we sampled, yes.
I Are there any characteristic differences between evolutionary strategies in terms of performance of the results?
Yeah, like you're saying empirically what happens. Yes, so they are slightly below the state of the art of actor-critic methods. Okay. I mean, they learn how to walk, etc., but they walk a little less good as with respect to the actor-critic methods. Now, this all depends on how much compute you are allowed to give them. Does this make sense? Also, this paper, I want to say that there is a lot of, how to say, tricks, implementation tricks that you need to do to get those things to work. What does this mean? It means that if you just grab a vanilla neural network architecture, you download, let's say, some model from a repository, and this model works really well with stochastic gradient descent, this model will not work well if you just dump it into this method, even if you have a lot of workers. What the authors saw is that once you start mutating the thetas, many thetas would end up in the same policy and doing exactly the same actions. So this is a pretty bad, the whole point of evolutionary methods is that once you mutate, you explore, okay? While they were not able to do this simply by mutating the parameter thetas because a lot of different neural networks would be mapped to exactly the same policy. Something that was for them very, very important, they call it virtual batch normalization. They say that it's very important to make the network output very sensitive to the input. Does this make sense? Very sense. So essentially, this virtual batch normalization is another way to normalize your input. Okay, so that slightly things change. You know, there is a huge change between at the output. All right. So there are these implementation tricks that came from this 2017 paper that said, okay, here evolutionary methods do also pretty well. So I would say it's an open research question. And for low-dimensional spaces, we already know that evolutionary methods do great, right? Now the research question is what happens in very high-dimensional spaces. And by the way, we're talking about intrinsic dimension. Like if the depends on the intrinsic dimension of the space. I mean, if you put a very deep network, you have more weights. I mean, if this is the same problem, you didn't change the intrinsic dimensionality of your space, okay? But basically, yes, so I would say it's an ongoing research question. We're not going to have a homework where we need to implement, I mean, potentially we may have some low-dim cross-entropy method of CMAS, okay, just to get an idea of how this works, because these are being used even right now, okay, and we'll see later papers that do that. My reason of showing this is to understand better the policy gradient methods and what do they do, and not to think of this score function estimator as something very exotic, because at the end of the day, it's only doing finite differences. So that's the reason that we're covering it here, okay? And yes, so far, we were sampling these epsilons completely random. What if, instead of sampling random epsilon vectors, we just sample one, and then we sample the antithetic one, minus you sample one and you put minus that one, okay, like those guys. So then you have these two thetas, theta plus, theta minus, okay? One goes in the one direction, the epsilon direction, and the other goes in the completely opposite direction of the epsilon vector that you sampled. And then you evaluate now your two mutations, you get rollouts, and you go to estimate your score estimator, the gradient estimator, which we already know that it's the reward multiplied with this theta minus mu, and we already know that the theta is going to have this particular form, mu plus sigma epsilon, so the mu will cancel, and sigmas will cancel, so eventually you have this. And what does this remind us of? This is a numerical, way of estimating the gradient, right? And we know finite difference methods, what do? They perturb one coordinate at a time. Okay, this particular j coordinate, for example, you try to estimate the gradient of a parameter vector in the j coordinate. You will sample plus epsilon, aj, minus epsilon, aj. What is aj? Well, it's the vector that has all zeros and one in this particular entry, all right? So, in our case, the way we sample in practice is not going to be based on each coordinate. Rather, we'll sample one epsilon direction and another antithetic epsilon direction, and we try to see how, let's say, the utility of our function changes as we change these parameters along that direction. Okay, so we sample different directions, and then we average based on the utility, and we take a step. That's all we're doing, right? Do you agree with this? Same thing also for, you know, in the action case, right? We take actions and so the difference then between evolutionary methods and policy gradient methods is where you put your noise. If you put your noise in your parameter space, and we call it here, this is your parameter theta, and then xi is the noise, and this your input noise, you know, sample from the zero mean and the identity matrix, identity matrix being the covariance, and this gives you the output theta, right? This is, and here is this epsilon grid, for example. You have an epsilon, and we have an alpha probability over actions, and then you have also the epsilon parameter that controls the noise. So you feed the noise, and then you get a new alpha. Okay, you sample. This is how you get samples from actions and samples from parameters, basically. So the only thing we're doing is we're sampling. We evaluate the utility of our samples. All right. Here the sample is on theta, but every theta, what does it do? It instantiates a policy. How do we compute the utility? We just do rollouts. There, if you change the actions directly, you sample the trajectory and you estimate the utility. So they're extremely similar. Now the question is, what is the right space to add noise? Okay, that's the question. Potentially you have a very long episode, and you know, it's very hard to assign rewards to different actions. Okay, basically you model the structure, but the structure is not informative. Yeah, sure, you think you have third trajectory, at the end of the day only the very last stage gave you any reward, right? Which somehow you need to figure out how to assign it to different actions. You don't have any hint of how to do that. And then potentially exploiting the structure is less useful, as opposed to a problem where at every time you have a reward. Okay, so you have much better idea of, you know, which action gave me that reward. Does this make sense? So the time the credit assignment problem is easier in that case. So then yes, it would make sense to exploit the structure of that trajectory. And there are some very recent papers that try to add noise in both spaces, action and parameters, and try to see, you know, how can we search in the best way, right, for our desired policy. Does this make sense what we're saying here? Okay, great. So the important thing is to know that in all cases we're just sampling noise, evaluating returns, and taking gradients based on, you know, the samples that we collected. There is nothing more exotic. Yes?
I'm just curious, is there any method to add noise to the state instead of action?
But what do you mean by this? How we're going to add noise to state?
For policy network, you add noise to action.
Right. So by state, like where you resulted, let's say, it's as if you try to change the dynamics of the environment. We wouldn't try to change the dynamics of the environment, right? Because a policy, no matter how you change it, you will never change the dynamics of the environment. Does this make sense? The only thing we care is, I have some theta, I have a policy. How can I get it better? How can I change the theta so that the utility gets higher? Okay. So the states.
Does it make sense if, like, at some step, I just teleport it to another step and just suddenly change it to another state and see what?
Right. So we cannot change trajectories. We cannot change. If this, imagine there is this state, and given this particular action, we always go to that state. This is the physics of the environment. There is no way you can change those dynamics. No matter what, as you push this pen to the left, this pen will always go to the left. Now, if for you going to the left is a horrible state, the only thing you can do is not to take that action. So you choose which trajectory to take. You cannot change the trajectory. You cannot change the physics of the world. The physics is what it is. You gotta. Does this make sense?
What if you're learning though? What if you're learning of physics?
Yeah, you better learn something extremely, you know, accurate, right? Because otherwise, I can make the model, the environment, to get me tons of rewards, right? That would be extremely maximizing my reward, but it will never happen because the environment is what it is. Does this make sense?
What if you do what you're saying for the initial state? So you're basically exploring from random initial states instead of from some fixed initial state.
Say it one more time, please.
So the idea is that, like, so that you're exploring more of the space, you start from random initial states, so you apply the theory that everything to epsilon is
Yes.
to the initial state, and that way you're exploring different parts of the space.
Yes, so this is very important. You need to be able to explore different parts of the space. If you're stuck on this particular part of the space, there's no way you will figure out what happens in the other part of the space that you'll never explore. Does this make sense? So those all are conditions that you are exploring efficiently. Does this?
Yeah, but I think saying that instead of using the random.
Oh, I see. This is what you mean noise. Yeah, like add noise in the initial states. That's exactly what we're doing with these multi-threaded agents, right? Each one is wakes up with he opens his eyes is in different parts of the environment because we do want to sample all parts of the environment. Okay.
But they all start from the same state.
Huh?
But they all start from the same state.
For the evolutionary case. No, they start from the same parameter vector. It's different, right?
They start an episode from the same initial state.
No, different agents don't need to start. They all explore different parts, right? You are trying to go up the stairs and I try to write on the board, right? Where did we see this in same initial state? Let's see. Did we see this on some slide or? Let's see. I think maybe, let's see here, maybe we see something. Let's see. Here we saw something. Initial parameters theta 0. Does this make sense?
I mean, but when you want to get F right,
Yes?
you need to run an episode.
You do, yes.
But they should all start from the same.
Right, so that's a good actually question, guys. So here we're all talking about the policy. Who controls in which state of the environment I am to start exploring, okay? The whole point of multi-threading is that every agent is going to end up in different state. Does this make sense? Okay. And indeed, that's what we want. We want different agents to explore different environments. Otherwise, if they all explore the swimming pool, all my gradients were going to be about the swimming pool. I go outside of the swimming pool and I don't behave well. Does this make sense? So the state where I'm going to throw you in the environment, the initial, is random. Now, once I throw you there, the dynamics you cannot change. Does this make sense? And so this all has to do with exploration. So I think what you're trying to say is the following. The most important thing is exploration. And here we're all talking about, forget about this, forget what is the initial state distribution, what are we going to do onwards. There's going to be special lectures on exploration. I think the first will be coming Monday from Professor Mitchell, who is going to go into details about this UCB that we took for granted when we were doing the sampling on the Monte Carlo research. And we will also have advanced exploration lectures, okay, that will talk about how do you take care of this, but I think you're trying to say is that we put an objective down, okay, which the most important part, which is exploration, doesn't appear in the objective, right? So I would like to say that when we cover the maximum entropy reinforcement learning, which hopefully will be coming Wednesday, we will see that we'll explicitly ask for the policy not to overcommit. The policy should, if there are, let's say, 1,000 different policies that all give you the same reward in this little environment, they should all be equally probable. Okay, so that you don't overcommit the policy in your current environment. And because your policy is so stochastic, potentially you will also explore better. Okay. Right. I think this multi-threading is all about, diversifying the states that you're going to end up on. Okay. Now the question is, once you're in a particular state, how do you improve your policy? Okay. So let's assume we took care of the exploration using this multi-threading. And in fact, the evolutionary paper says, you know what, with so many threads, my explorer is so much better. You know what I'm trying to say? It's so much better than this epsilon greedy because I changed the vector thetas and the dramatically different policies result, and so I can explore a lot. While if you're in the epsilon greedy and you change an action with an epsilon probability, you don't essentially, explore. You're potentially stuck there. Okay? Right, so the state transitions we cannot influence, but the initial state distribution, yes, can be whatever you like it to be. Okay, all right, so we already talked about this paper. In fact, the way they discretize their continuous actions is just to explore better. So all the time this exploration is hidden in all the papers, all the objective is about how I'm going to take gradients on my policy neural network, and the exploration is as a side effect. But I say that we're going to see in later lectures, it's an ongoing topic of research how to unify exploration and just exploitation, which is taking the best gradient right now, based on what you've seen, okay? We saw this. Okay, so how would we go to implement on PyTorch or TensorFlow some standard policy gradient method, okay? You're definitely going to go there and write the sum over trajectories. How will the, automatic, this differentiation software figure out how to put the gradients and that you want to use this particular gradient estimator? What you're going to do is because you know you want this gradient estimator, you want this particular gradient estimator, what you're going to do is you're going to write this loss function, okay? You see there's no grad there, and the grad will come out from the algorithm just trying to maximize this loss function. Does this make sense? That's how I would write it. So now we go inversely. So we had an objective, we say, ideally that's what I want to maximize. Then we said, okay, unfortunately it's not differentiable, so let me use this gradient estimator. And I will say, okay, this is my gradient estimator. What should I write into my deep learning package to, take gradients based on this gradient estimator? Okay, that I decided. Correct? Now, here is another equation. And you say equivalently, this objective right here that came from inversing the gradient estimator is equivalent to this objective. Why this is the case? First of all, that's number one. And now, why do we care about it? Why do we care about it? Well, we care about it because when we update the policy, we update sequentially, so we always have a theta old, and we try to see where we're going to step to get the theta new. Okay, so we will be using this type of objective. A few methods that we're going to see next use this type of objective. Why this type of objective is identical to the previous objective? Okay. Well, here is again our objective. Expectation with respect to trajectory sample for my policy of the utility of the trajectories. Yes, I can write the expectation explicitly using a summation over trajectories and probability of those. And now, what we know from importance sampling, okay, is that I can rewrite this in the following form, where the trajectories are sampled now from a other policy. I care about the policy theta, but imagine I have an older policy, theta old, okay? And how can I write the same objective while having still an unbiased, I haven't changed at all the expectation? So I multiply and divide with this pt theta old. And do you see what I mean? This is how we derive the importance sampling equation. What happens from row 2 to row 3 is we multiplied and divided with the probability of the trajectories to an alternative policy. Okay? Now, we see that this looks like an expectation. It's a summation with the probability. So you can just remove this probability from there and just put it here on the sampling. So we're saying a summation over trajectory sample from the old policy of this guy. Okay, we have this ratio of probabilities. And sure, this sum can also be written as the expectation. And here we go. Do you see? So this is and now if we take the gradient of this objective, how it's going to look like? Well, the gradient with respect to theta, the only term that depends on theta here is here, this guy. We take the gradient with respect to theta with respect to theta old. Essentially, what is this? If you look at all this, is the grad of the log of the probability of the trajectories evaluated at theta old, right? Because this is 1 over the function evaluated at this particular point that I care to take the derivative, multiplied with the derivative. Okay? Do you agree with this? Let's look at it a bit more. So the first set of equations just rederive importance sampling. Okay? So what we see is that when I care to take an expectation of a particular quantity, here which quantity I care about? Which quantity I care about? The returns of my trajectories, all right? And I don't have access to this particular distribution, which is the policy theta with parameters theta. I don't have access to this. I have access to another policy with parameters theta old. What I can do is I can sample from the theta old, get trajectories, look at their utilities RT, the returns, but make sure I weight them using this ratio. Okay? How probable is the trajectory under theta versus, divided by how probable is from theta old. So if it's very probable under theta, you should weight more. All right? This is just important sampling. And given the homework you have the homework too somewhere, this should be kind of a, yes, sure, it makes sense. I mean, we don't know yet why we're doing it, but yes, it goes through, right? Great. And again, I'm just saying, take a gradient of the expectation here. By the way, yes?
So if you have theta old, how do you know what theta is? Like if theta old is your current subparameters?
Yes, you do not know. You just know the analytic form of the policy, right? And you have it evaluated in a particular theta old point, and you don't know what theta is. Theta is just a variable right now, all right? It's a variable. Theta is a variable.
Okay, so then how do you know what the ratio is in that case?
Well, here, our gradient is just gradient of the log of this. So it's an analytic form here. Do you agree that there's an analytic form? Imagine that it's a neural network. There is some mu, Gaussian, the log, they're going to kill the expectation. Just the output of the network here, evaluate the theta old, right? It's just the gradient, and then you evaluate the gradient of theta old, right? Right, so if we just focus on, how can we maximize that objective, this is what happens, all right? Theta is a variable, and I take the gradient with respect to theta, and I'm going to sample trajectories from theta old and evaluate the gradient of theta old. Let's see, maybe if we move a little bit forward, maybe things are going to make more sense. Let's see. So again, nothing happened here. It's just I went from trajectories again to actions. And again, the advantages here are temporal. There is no critic here. As you see, this advantage is just the estimation of the advantage from t onwards. No critic. There is no critic here. Great. So since the two are the same, let's consider. We say yes equivalently. Sounds good. Now for now, we'll forget about it somehow. But let me tell you what we're going to discuss. We'll say that a big problem to whatever we've said so far is that we don't know how to take a step size. Yes, we computed the gradient, but how much do we need to move on that gradient? Okay? And then you're going to say, yes, but it's always like this. I mean, supervised learning also, I don't move forever. It's, it's not a convex objective. You need to make small steps. You have learning rates. You have schedules with your learning rate. You also, vary your hyperparameters. Try to figure out what is the normal step size. There are different optimization methods, RMS properties, and that to help you to take good step sizes. So the problem is that here the choice of the step size is more critical than in supervised learning, because as long as you make a bad step, you're going to end up in a bad policy. You're going to collect bad data because you are on policy, right? And you are never going to recover. In supervised learning, wherever your weights are, does not affect your data, like X and labels. It's the same. The data stays the same. Here, because the data depends on your model, things are more fragile. Okay? So that's why how we're going to take a step size is a big deal. And people have empirically, so by the way, for now, forget about tactical critics, just think about, we have this reinforced type of rewards. And people have seen empirically that if you choose one step size and you try to keep for the whole optimization, it's no good. And now I'm going to say, okay, what's the big deal? I'm just going to take tiny little steps. Okay? Yes, you can take tiny little steps, but then you are not going to use your experience efficiently. Okay? So you are going to improve very, very slowly, and because when you write a paper, you show performance and samples, your curve is going to be very low. Doesn't make you try to push this curve high. Okay? Alright, so here is the GD, theta nu. It's all about this epsilon here now. Now we know the G. We discussed a lot about G, now we're going to talk about the step. So this is, sorry about this. So this is gradient descent in parameter space. You have some loss, and you try to minimize the loss. And by definition of the gradient descent, you try to find a direction d that if you step along this direction, what does it mean to step? Theta plus d. You change your parameter along that direction. If you stay within a ball of epsilon, things are not going to, you're essentially going to minimize your objective. Okay, so it's a small local optimization you're doing. All right, this is by definition of this, steepest descent direction. This is the definition of the steepest descent direction. So what do you see here? That the Euclidean distance, the parameter space, influence your optimization. Does this make sense? How far away your parameters are to each other influences. Is this the right way to do it? And no, it's not. Why? Like, look at these two Gaussians here. Their means are both 4, like this dx is 4, okay? But because they're very different distributions, the change of the distribution is very different. So you have some parameters. This parameter has some distribution. For example, our policy. Parameters change and the policy changes. And what gradient descent tells you in parameter space, the standard gradient descent, is that change moves so that your Euclidean distance of your parameters is kind of small. But the thing is that you don't care about how far the parameters between each other. Why do you care about this? The only thing you care is the resulting distribution should not be too far away from each other. Because if the resulting distribution is too far away, then whatever advantages you estimated with the first policy will not be at all folded for the next. The previous policy will not hold at all for the next policy. That's why we don't want to take gradient descent in the parameter space. That's why they say, it all depends on the parameterization of your distribution. We want to take steps in distribution space. Does this make sense as a motivation? Why we don't care to do standard gradient descent, but rather we want to think how my distribution is going to change? It's all about how you link your parameters theta to your probability of your distribution. Okay, great. So this motivation I think makes a lot of sense. Now the question is, great, in parameter space you have Euclidean distance. In distribution space, what distance we're going to use? Yes, how do you know? KL we're going to use. That's right. Very simple. So basically what we're going to do, instead of defining the step size in terms of this Euclidean ball, the parameters, which makes no sense, like intuitive sense, it doesn't make any intuitive sense. As you change the parameterization of the network, this completely can be small, big, you don't know. All right, a lot of tweaking you need to do to get this right. We're trying to make things automate. We're trying to take things from the heuristics and the implementation details to the algorithm now. To have a way of how to take your gradients that will not go into the implementation details of the paper and the scheduling and the etc. etc. Okay. So you will instead define the D so that the KL divergence between the previous theta old and the new is equals to C. Why equals to C and not smaller than C? Because you want to be able to make some progress, let's say. Okay, so you want to minimize your objective, otherwise you're just going to stay in the same place. Okay? No, because you're trying to minimize this, so even if you put smaller or equal to C, you'd be fine. The KL divergence is not exactly a metric. A metric is supposed to be symmetric. KL is not symmetric. You see here the 0 when the two distributions are the same, otherwise it's positive. However, if the two distributions are very close to each other, it's almost symmetric, so it's okay. Let's just take it. Okay? Let's just take it. We'll take it. Okay. Now what are we going to do now? Let's see. It is not that difficult. You take the constraint and you create this unconstrained objective because we'll put this as a penalty. Standard Lagrangian multipliers. You put this Lagrangian multiplier lambda, KL minus C. Okay? And you're going to start taking gradients with respect of this object using Newton method. In particular, we are going to approximate both our losses and our KL in terms of first order and second order approximation. Right? This is standard gradient descent. Here is the first order approximation. The loss in current place plus the the first gradient multiplied with d. D is what we're trying to find. Plus, this is supposed to be the second order Taylor expansion of KL. And this is what we're going to look at now. How do we write the second order Taylor expansion of the KL? For now, let's assume we have it, okay? And let's assume it looks like that. And you know what? This is the Fisher matrix. Amazing. Now, if we had this, so that we try to demystify this natural gradient, what would you do to pick the d? This is a quadratic problem. Okay, what are we going to do? Set the gradients to 0, right? Then you know you found the minimum. You agree with this? Okay, let's take the gradient set to 0.
So what is your intuition to assume this?
1 second. What do you mean? So what you're saying, for example, let's see. First of all, that's what we always do in optimization, right? When we have a non-convex objectives, we try to do some Taylor approximation, first order, second order, and take gradient. There's nothing exotic there. Now what you're saying is that where did the second order term of the L go? Well, it's negligible, it's very small. Okay? It's very small. Let alone that it takes long to compute it. Same with the Fisher matrix, by the way. But there are fantastic recent papers, 2017, excellent performance. I think somebody asked here, is natural gradient used nowadays? Yes, there is this fantastic paper, 2017, I'm going to show it at the end, that found a very smart way to estimate this Fisher matrix very fast, or approximate it very fast. And then, because you know it's a Hessian, like number of parameters by number of parameters, this is huge to estimate, huge to store. That's why we like first order methods, so that we don't need to have these big matrices, okay? Now, okay, so we throw away the second order of the loss, that's okay. Other than that, I don't see any exotic thing here. We just take Taylor expansion, that's what we do. We have a non-convex objective, we take some second order approximation, we take gradient step, we're done. Do you agree?
So you mean that the 1 over 2 lambda the transpose FD is...
Oh, this one, forget about this. So this is going to be a whole slide that explains this. Okay, so this guy is the Taylor expansion of the KL term. There's a whole slide about this. Okay, so we take a KL, and what do we say? We say KL of P theta condition P theta plus D equals what? The KL of P theta condition P theta, where we are right now. How much is this? 0. Plus expectation of this is the first order plus second order. The first order, it turns out it's also 0. And the second order, it turns out it is like this. Do you see what I mean? So we're going to go into this. Okay? So just the only thing I want to say is that this guy, and I'm going to make potentially symbols. So this guy goes here. This is the first order Taylor of the loss. And this is the second order Taylor of the KL. Okay? And somehow the first two terms of the Taylor expansion of the KL are 0 and disappear. So you have only the second order term. Okay? So there is no choice there. It's just the math works out like this. Great. And then what do you do? This. I just want to show to the end here. We set it to 0. We take, right, the gradient. Sorry, this is argument with respect to D, right? Yep, argument with respect to D. And so the gradient direction ends up being this. And it looks like that. And here is this Fisher matrix. And this is called the natural gradient. Do you see how nicely it's motivated? Do you see how nicely it's motivated? It's motivated by the fact that you don't want to take steps in your parameter space. You want to take steps in your distribution space. So you want the conditioning, this ball should be measured in the KL of distribution as opposed to your parameters. Okay? And the only thing we need to discuss in the next course is where did this we're going to go through the Taylor expansion of the KL. Don't worry about this. We will have a lot of things. Well, okay, yes, but the only thing, this is not going to take at all a long time in the next lecture, but here is TRPO. So probably you hear all the time TRPO, right? There are some nice theoretical results that under some, if you take a step now, you increase your policy, okay? Which eventually at the end of the day, the practical algorithm does not follow the theoretical result, but it doesn't matter. But it is exactly what we discussed. There is a KL constraint, there is this objective, okay, which we saw because it's equivalently right. Does this make sense? So, very simple. 1 second. I want to show you. Okay, that's fine. Don't worry about this. We will go through it in the next time. But basically, all this TRPO and PPO is about step sizes. We'll continue. We'll take 5 minutes in the Wednesday lecture to finish this, and then we'll go into max entropy. I think a lot of things became more clear today, hopefully, right? We will go through this 10 minutes in the next lecture, so don't worry. And we'll see the KL Taylor expansion to see why this D transpose blah D came out, okay?
The same for the definition of F.
All of this will be the next lecture. Why this is the Fisher matrix and how the KL became the Fisher matrix, blah, blah, blah. Okay? Sure.